There's a specific way we're supposed to like put our name on it? No, just make sure it's on it. Okay, and I was able to do whatever you want to say. Kind of small and at least. Hiding it.
Oh, I thought it was gonna be in the bottom. No, no. I thought that was like.
Oh, no.
Oh, no.
No, that's just someone's, yeah.
Oh, I thought that was like an example of.
No,
I was scared. I was like,
no.
oh, my name isn't on the front big bold marker.
All right, so let's get started. I hope everyone had a good long weekend. If you haven't already done so, please bring your assignment up at the front. And then if you haven't noticed already, I've posted assignment number 2, and so you can find that on the course website. We've covered everything you need in order to complete assignment 2, so you can go ahead and get started on that. And then last reminder is there's no lab this week, so no labs tomorrow. We'll resume the regular lab schedule next week. The reason is just we need to cover a bit of material before we get into lab number 4. And in fact, the stuff we're about to start covering is sort of, we're going to get into what I consider to be the meat of the course. Today's class will be about kind of motivating why we're going to develop these new methods starting next week. So we're going to start introducing new mathematical concepts that will help us analyze our circuits. And so today, we're going to try to analyze this RC circuit that's driven by a sine wave. And the goal is going to be to try to figure out what is the current I. Now, if you think back to lab number 2, the last part you looked at this exact RC circuit, and we looked at, say, the signal generator output and the voltage across the resistor, which is just I times R. So the voltage across the resistor is essentially the current. It's at least proportional to the current. And one thing we saw is that the current oscillated at the same frequency as the function generator. So we know they're going to have the same frequency. The phase of the current, or the voltage across the resistor, was not in phase with the function generator. So there's going to be a phase shift, which we're going to have to try to find. And you may not have noticed this, but if you were to adjust the frequency of the signal generator, the amplitude of the current would change. So the amplitude is also going to be frequency dependent. And so we're going to try to find that as well. So what we did, we started this process, and all we've done so far is consider a Kirchhoff loop rule. So which says that, okay, if we gain the voltage Vn and then we drops voltage across capacitor and resistor, that gets us back to the starting point. The voltage across the capacitor is Q divided by C. The voltage across the resistor is I times R. And so this expression must total 0. So right now we have an equation that mixes charge and current. We would like to solve for one variable. And so what we can do is we can take the time derivative of every term in here. So we get the derivative of Vn minus 1 over C dq dt is the current, and then we have a di dt term. And so this is the differential equation that we're hoping to be able to solve. We're going to take advantage of the fact that we know some things. We know that Vn is some amplitude times sine omega t, where omega is 2 pi times the frequency. So I can just evaluate this time derivative, right? The sine's going to become a cos. We also know that the current is going to take this kind of form. It's going to have an amplitude at same frequency as the function generator, and then a phase shift. So if it's going to have that form, I could also take the di dt, I can evaluate that. And so that's the starting point. And the ultimate goal is, if I want to know the current, the things that I don't know about it are its amplitude I naught and its phase phi, and in particular, how those things depend on the frequency. And so that's what we're going to try to figure out. Okay, so let's start by evaluating dVn dt. And so let's see, the sine becomes a cos and we pick up a factor of omega. So that's going to be omega v naught cos omega t. Okay, now let's evaluate, the other thing we're going to need is the di dt. I mean, it's essentially the same thing. We take the derivative, the sine becomes a cos, we get a factor of omega. Okay, so we're going to end up with omega times I naught cos. Sine becomes cos, cos omega t plus 5. Okay, good. So we're going to sub these into, let's give this expression a name, number sign. We're also going to sub these into that same equation. All right, so let's see what happens when we do that. It's going to get messy before it gets cleaner, but that's okay. All right, so the first thing we have the derivative, so of Vn, so we have omega V naught cos omega t. And what I'm going to do is we have these minus signs. I'm just going to move this stuff over to the right. So we'll get rid of the minus signs. So then we'll have 1 over c times the current. But the current, we have a form for that current. So it's going to be I naught divided by c. And then it's just going to be sine omega t plus 5. And then we're going to have plus r times the derivative of the current, and so the derivative of the current is here. So it's going to be plus omega I naught r, and then the sine became a cos. All right. So to go further, what we're going to use is we're going to use some trig identities. The problem that we have right now is that over here, we have a cos omega t, and over here, we have cos omega t plus 5. I might be able to do something if I had terms that were just cos omega t, and I can get that by using the following trig identity. So let's use the following trig identities. As we do this, I just want you to keep in mind that this is a pretty basic circuit. It's just a resistor and a capacitor and a sine wave. And so all of this work we're going to do is for basically one of the simplest circuits that we could imagine that's not just resistors. And so it's going to show you, I hope, that there's a lot of algebra and a lot of work to solve this problem. And so we're going to want to have some tools that are going to make this more efficient. Okay, but for now, let's just use these identities. So we have sine of like a plus b, where a is omega t and b is phi. We could rewrite that as a product of sine omega t and cos phi plus cos omega t sine of phi. We also have a cos omega t plus phi. And this one is a product of coses minus a product of sines. Okay, so the sine identity will go into here, and the cos identity will go into here. Okay, so let's see what happens if we do that. So omega v naught cos omega t, nothing happens on the left. But on the right, we're now going to have a big messy thing. So we need the sine identity. So sine omega t cos phi plus cos omega t sine phi. Okay, and then we have another term. It's plus omega I naught r. And now we need the cos identity. Let's see. Cos omega t cos phi minus sine omega t sine phi. All right. So we've got some now terms. We have 5 terms in this expression. 3 of them have cos omega t factors, and 2 of them have sine omega t factors. So we'll collect those common factors. So wherever we see cos omega t, we're going to bring those together. And wherever we see sine omega t, we're going to try to bring those together. All right. And so what do we get when we do that? We'll start with the sine omega t. All right. So we have I naught over c cos phi. So I naught over c cos phi. And what else do we have? We have a minus omega I naught r sine phi. So minus omega I naught r sine phi. Okay, I think that is right. And then we're going to have our plus cos omega t. So which one should we start with? Let's start with this one. I naught over c sine phi. And then we have a plus omega I naught r cos phi. Plus omega I naught r cos phi. And then we have this one. I'm going to bring it over to the other side. So we'll have a minus omega v naught. And because I brought that term from the left over to the right, all of this would have to be equal to 0. Okay. Now, we haven't made any approximations. This is so far an exact solution. In fact, we won't make any approximations. But if you think about this, what we've got is some signals, voltage and current oscillating in our circuit, and this has to be valid at any time we pick. I could pick a time, say t equals 0. When t equals 0, cosine's 1, sine is 0. So this is all going to vanish, and this is going to become a 1. And it still has to be true that the stuff in this brackets has to equal 0. And then I could go pick a different time. I could pick the time where omega times t is equal to pi by 2. If I do that, the sine function will be 1 and the cosine will be 0. In that case, all of this is going to vanish. This is 1. It still has to be true that everything in this first square bracket has to be 0. Okay, so this expression must be valid at all possible times that you could imagine. So at some times, we will have, say, sine omega t is equal to 0, while cos omega t is equal to 1. So when that happens, it must be that, what did I want to call this? Let's call this, so in this case, bracket 1 has to be equal to 0. Okay, so at other times, we will have the opposite. Sine omega t is equal to 1, and cos omega t is equal to 0. In this case, we will require that 2 is equal to 0 where I will call this 2. All right. Okay, so let's start with the easier one that has only 2 terms is this second one here, the one that multiplies by sine omega t. So let's start with 2. And all we're going to do is we're going to set 2 equal to 0. Let's see if I can get it here. It's I naught over c cos phi. So I naught over c cos phi minus omega I naught r sine of phi is equal to 0. Okay, well, that's not so bad, actually. One nice thing that happens here is that both terms have I naught. So if I eliminate I naught, I divide by I naught, 0 divided by I naught, still 0. Now I have an expression that's only in terms of a single unknown, and that's phi. Okay, so let's see if we can solve for. So we've eliminated the unknown I naught, the current amplitude. So let's solve for phi. Okay, so what's that going to look like? 1 over c cos phi is equal to omega r sine of phi. I can do sine divided by cos to get tan. So therefore, tan phi is equal to, I got to divide by omega r, so it's 1 over omega r c. Oops. Or if we really want just phi, that's going to be the inverse tangent or the arctan of 1 over omega r c. Okay, good. So we've got one of our 2 unknowns. We now know how phi depends on frequency here. Let's keep going. And let's see if we can make some progress on the second equation, which we happen to label equation 1. Before we do that, we're going to have a bit of a problem because it's going to involve sine phi and cos phi and a third term that doesn't have any trig functions. So we're not going to be able to do the same sort of thing that we did before, where we say, well, let's take a ratio and we'll construct a tan phi somehow. It's not going to work this time. We're going to need to know some expressions for cos and sine of phi. Okay, so before tackling 1, we will need to know cos phi and sine phi. So here's where we're going to be a little bit clever. All right. We know tan phi, it's right here, and we know some properties of tan phi. So what we're going to try to do is we're going to construct a right angle triangle from tan of phi. And so we know SOHCAHTOA, right? Tan is opposite over adjacent. And that's, we know tan phi is also 1 over omega RC. Okay, so what we'll do is we'll say, I'm going to make a right angle triangle where there's going to be an angle phi. The side adjacent to phi, I'll make that a length omega RC. And then the side opposite of phi, I'll make that a length of 1. So let's see if we can draw this right angle triangle. So it's going to be something like this. I have to put phi somewhere, so I'll put it over here. So the adjacent side, we're going to make omega RC. the opposite side will assign a length of 1. And then that allows us to calculate the hypotenuse, opposite squared plus adjacent squared square roots. And so it must be the case that this is equal to 1 squared, which is 1, plus omega RC squared. And then take the square root of all of that. Okay. Well, now I can calculate cos and sine, right? Cos is going to be what? Adjacent divided by hypotenuse. So with this triangle, we can now find, okay, cos phi is equal to the adjacent of the hypotenuse, omega RC divided by the square root of 1 plus omega RC squared. Okay, and then the sine of phi is the opposite over the hypotenuse, so it's 1 divided by that square root. All right. So now we can go back to equation 1. And we can substitute in these expressions for cos phi and sine phi. So let's sub these expressions into 1. All right. I need to remind myself of what equation 1 was. Where did it go? There it is. So it's I naught over C sine phi. So I naught over C sine phi. Not over C. And for sine of phi, we put 1 over the square root of 1 plus omega RC squared. This is sine phi. Okay, and then I think it was plus omega I naught R, if I'm not mistaken, times cos phi. The cos phi is omega RC divided by the square root 1 plus omega RC squared. Okay, and then there was a third term. Sorry for scrolling, but the third term was just minus omega v naught, and all of that's going to have to be equal to 0. So it's minus omega v naught, and that has to be 0. Well, this is pretty convenient because now we have an expression where the only unknown is I naught. The frequency is something I set. I pick my parameters R and C. I can set the amplitude of my voltage. And so I know I control all those things. So we just have to solve for I naught. So this expression only involves I naught. We can solve for it. What I mean by only involves I naught is there's no phi in there because we replaced cos phi and sine phi with these expressions from our right angle triangle. So I'm going to leave this as an exercise for the student. It's just a bit of algebra. Exercise for the student is to show that I naught is equal to omega v naught times C divided by square root of 1 plus omega RC squared. And let's just summarize the other important result, and that was tan phi was 1 over omega RC. And so now we know everything about our currents. So therefore, we now know the current I was I naught sine omega t plus 5. Okay. This circuit, yeah,
So isn't the tan relation only true when the first term equals 0?
no,
No?
nope, this expression that we came up with right here, this has to be valid all the time. So if we, sorry, where did it go? This is not the one I wanted. This is the one I wanted. This has to be true always. Notice that in here and here, there's no time at all. All the time dependence is here and here. So if this is equal to 0 at one particular time, it's always equal to 0. And if this is equal to 0 at one particular time, it's always 0. Yeah. Okay, this circuit that we've been, yeah, go ahead. Has no phase? Oh, the phase of the input is arbitrary, right? I can only measure phase differences. I can't, like if I just have a sine wave, I can't tell you what the phase is. I can only tell you that if I have two sine waves, they're out of phase by a certain amount. So I can arbitrarily say my voltage has a phase of 0, and the phase of my current with respect to that voltage is going to be given by this expression. Yeah. Okay, so this circuit, this RC circuit that we've been thinking about, it actually has some practical uses. And so practical use of this RC circuit, which is driven by sine wave. All right, so to see this, what we're going to do is I'll draw the circuit again, and we're going to consider the output as being measured across the resistor. So what we started with was our function generator. Vn was V naught sine omega t. And then we had our capacitor and our resistor like so. So here's C and here's R. And what I'm going to do is I'm going to measure the V out across the resistor. But the voltage across the resistor is just I times R. Okay, and we just solved for I. So here's I. Okay, so, well, let's see. V out is equal to IR is going to be equal to I naught times R times sine omega t plus 5. Okay, so what I want to do is I want to think about just the amplitude or the coefficient in front of the sine omega t. Sine omega t, we know it's just an oscillation. This coefficient tells us how big that oscillation is. So let's consider the amplitude of the out, which is given by, well, it's just I naught times R. But we just solved for I naught. There it is. It's omega V naught C divided by the square root thing. So this is just equal to omega V naught. And then I have to multiply by R, so I'll stick it in there. So omega V naught times R times C divided by the square roots. Okay, so there it is. We could also evaluate the ratio. Ratio of the output amplitude, which is I naught R, divided by the input amplitude, which would be, say, V naught. Okay, so that ratio, I naught over R, or I naught R divided by V naught. All we have to do is just divide by this V naught. So it's omega RC divided by the square root. So it's omega RC divided by the square root of 1 plus omega RC squared. Okay, good. This is where I wanted to get to. And so what we're going to do is we're going to try to see if we can plot this. And we're going to plot it by considering a few special cases. One special case is the frequency is very low. What does very low mean? Very low is going to mean that this omega RC in the denominator is much smaller than 1. And then we'll think about, well, what happens if the frequency is very large? Okay, if it's very large, what that's going to mean is that omega RC is much bigger than 1. And then we'll consider the third special case where we're at an intermediate frequency where maybe this 1 is equal to omega RC. So we will consider 3 cases. And so there's going to be omega RC is small compared to 1. Omega RC is large compared to 1. And omega RC is equal to 1. And so we'll call that, I think I'll call that a special frequency. Sorry, I wanted that to be equal to 1. So this is some special frequency. We'll define what we mean by the subscript C in a second. I guess maybe let's just leave it as omega RC is equal to 1 for now. All right. Okay, well, you tell me what's going to happen when omega RC is really small. What's going to happen to this denominator? Yeah, it's just square root of 1, which is just 1. Okay, so if we call these cases 1, 2, and 3. So 1. For omega RC much less than 1, the square root of 1 plus omega RC squared is approximately equal to 1. Right? We have a small number squared, which is really small compared to 1. And so the 1's going to dominate. So in that case, this ratio of amplitudes is just going to be omega RC. And we already know that this is a small number, so we just maybe emphasize that this is small. We're going to do the other cases. Let me start a plot here. I'm going to make a plot of this ratio of I naught R, the output amplitude divided by the input amplitude. I'm going to make that plot as a function of frequency. Now we saw that at low frequencies down here, it was just equal to omega RC, which is a linear function. So it's going to start out linear. So this goes as omega RC. Okay, so that's what we know so far. All right. So case number 2 is omega RC is big. What's going to happen to the square roots when omega RC is large? What's 1 plus a very large number? Just the large number. So the 1 we ignore, we have the square root of a square, and so this is going to be omega RC this time. Okay, well, what does that mean for our amplitude ratio? we have omega RC divided by the square root, but the square root's just omega RC. So that means that this ratio becomes 1. So this is approximately omega RC over omega RC, which is equal to 1. All right, so if we go back to our plot here, then out here at high frequency, we're at this point 1. Oh, shoot. Okay. Good. So the third special case was omega RC is equal to 1. In this case, we're going to get the square root of 1 plus omega RC. Well, if omega RC is equal to 1, then we have 1 plus 1, and so that's going to be root 2. And so in this case, our amplitude ratio is going to be, so what was it? It was I naught R divided by V naught was equal to omega RC, but omega RC is 1, so it's just 1 over root 2. Okay, what's root 2 is like 1.41. 1 over root 2 is 0.707. So somewhere on our axis here is the 1 over square root 2. And so what's going to happen is we're going to have a point that sits here. And this is going to be when omega is equal to, omega RC is equal to 1. So omega is 1 over RC. I'm going to call it now omega C is 1 over RC. And then what we have to do is we have to smoothly join these 3 parts of our curve. And so it's going to be something like this. Sorry, it doesn't go above 1. It stays below 1 always. All right. And so what I want to see from this plot, what I want to take away is that at low frequencies, our output is small. It's suppressed, attenuated. At high frequencies, our output is the same size as the input because the ratio of amplitudes is 1. And so this is a type of filter. This is called a high pass filter because it attenuates at low frequencies, but passes without any attenuation at high frequencies. Okay, so this is no attenuation of output. And here we have strong attenuation of, I guess I can be clear, output amplitude. So this is called a high pass filter. So if you wanted to make a low pass filter, what might you do? What could you do differently? We're measuring right now, we've measured the output across our resistor. If we have no voltage dropped across our resistor, where is all the voltage? If we're at low frequency, we have an RC circuit, our resistor has very low amplitude. Where's all the amplitude? It's across the capacitor, that's right. So when we have weak signals across our resistor, we're going to have strong signals across our capacitor. And vice versa. When I have a strong signal across my resistor, my capacitor has to be small voltage. So if you were to measure instead the voltage across the capacitor as your output instead of the resistor, you would make a low pass filter where you pass without attenuation at low frequencies and then attenuate at high frequencies. Okay, good. So all of this is true. It's all correct. What I want to emphasize is that this took us to analyze a simple circuit. What did it do? It took us 1, 2, 3, 4 pages of algebra before we started talking about the application. And so I wanna cut that down. Sorry, I said I was gonna tell you why I put a C here. This is called the cutoff frequency. And so roughly speaking, frequencies below the cutoff frequency are attenuated, and frequencies above the cutoff frequency are passed. Of course, it's not a sharp cutoff, it's gradual, but that's kind of a rule of thumb. Yeah.
So a low pass filter as a measuring capacitor would just be the exact same graph, but the other way, right? It would just be going down next.
Yeah, it would be 1, and then once you got to wherever RC sits, then you get integration. Yeah. Exactly. Okay, so we got about 10 minutes left. Let me just introduce the next topic. So solving the RC circuit driven by a sine wave wasn't too difficult, but it involved lots of algebra, trig functions, and a little trick to find cos phi and sine phi. Right, that little trick was just constructing that right angle triangle. Now you could imagine the next step, in fact, in lab 4, what we're going to do is we're going to have a function generator outputting a sine wave, a resistor, a capacitor, and an inductor. And now it's going to be even worse because now I'm going to have a third term in my differential equation, and it's going to involve a second derivative of the current. And so things just get harder. It's still possible to use the methods that we did to solve that entire problem. But I don't want to do that. I want to find a better way to tackle these types of problems. So we need some new mathematical tools so that we can solve these types of problems more efficiently. Okay, so I can tell you now that the kinds of things that we're going to do are, we're going to introduce complex numbers. And I don't know, have you guys seen like Taylor series already? Yeah, Taylor series. So we'll review Taylor series, and then we'll eventually we'll combine those two things to get at Euler's equation, which you may have heard of. That's the e to the j is cos, e to the j phi is cos phi plus j sine phi. That leads to what lots of people claim is the most beautiful equation in math, which is something like e to the j pi is equal to -1. Okay, so we're going to do all of that, and we'll do it in a couple of classes. So let's start with develop the idea of complex numbers. Okay, so the definition you probably have seen already. It's just that the square root of -1 is equal to plus or minus Usually people use I. In electronics, we use J because I is reserved for current. Okay, but anyways, it's just the normal definition of the square root of -1. So let's check. So if I take the square root of -1 and I square it, I get -1, and that's equal to plus or minus j squared. And so that's equal to just j squared. And so we get j squared equals -1. And that's what we'd expect. Okay, so that's just a pure definition. There's really not much interesting there. Let's see why this is a useful tool to have to solve some problems. And we're going to start by thinking about not electronics, just a simple math problem. Okay, so why is this definition useful? Okay, it allows us to solve some problems that previously had no obvious solution. Okay, there's some easy examples. Let's consider, what if we ran into a problem where we needed to evaluate the square root of -36? Well, what I can do is I can write the square root of -36 as the square root of -1 times the square root of 36. And now we can say, well, this I'm going to call j, and this I'm going to call 6. And so the square root of -36 just turns out to be 6 times j. In fact, it could be plus or minus. So you could put plus or minus on either one of those things. Okay, and then if you square it, the plus minus 6 becomes 36. The j squared becomes -1. You recover your -36. All right. So let's do another example, one that's maybe a little more interesting, maybe not much more interesting, but a little bit. So let's consider x squared minus 2x plus 4 is equal to 0. So just a quadratic equation type problem. Well, what we know is that the solution for x is going to be minus b plus or minus the square root of b squared minus 4ac over 2a. So we have a is the coefficient of x squared is 1. B is the coefficient of x is -2, and then c is the 4. Okay, so x is equal to minus b, which is +2, plus or minus the square root of b squared minus 2 squared minus 4. A is 1, c is 4, and then divide by 2a, so we divide by 2 times 1. Okay, so we get 2 over 2, which is 1, plus or minus, let's see, this is 4 minus 16. So what's that, -12? So it's the square root of -12 divided by 2. Okay, so x is equal to 1 plus or minus square root of -12. I could write that as square root of -1 times the square root of 3 times the square root of 4, and then we have our 1/2. So we'll cancel the root 4 and the 2, and the -1 becomes j, and so we get that x is equal to 1 plus or minus j times root 3. Okay, so what we're going to do is let's just check this answer. This will be the last thing we do. Let's check it. So if this is a solution, we expect x plus 1 well, what did I do? How did I want to do that? Do I really want to check this? Okay. We'll do it this way. X minus 1 plus √3 times x minus 1 minus √3. So those are the roots of our equation. If we multiply this out, hopefully we'll get our original quadratic back. Okay, so let's do this. We get minus x times 1 minus √3. Well, why don't we start with the x squared? So x times x is x squared, x times this thing is minus x times 1 minus √3. And then we have minus x times 1 plus √3. And then we have, let's see, we have to multiply these things. I'll just write it out. So it's going to be plus 1 plus √3 times 1 minus √3. Okay, so let's see, there's going to be some cancellation. We're going to have minus x times minus √3, so that's plus √3x, and we got minus √3x. So these ones are going to cancel. And what do we get? X squared minus x, so it's minus 2x. And then what do we get? We get 1 times 1 is 1. 1 times minus √3, √3 times plus 1. The √3s will cancel, the cross terms cancel. And then we get minus √3 times 3 is minus 3. And so what do I get? I don't think that's going to work. This is 1 minus 3. I thought I had a 4. Didn't I start with a 4? Why isn't it plus 4? I must have made a mistake. Does anyone see my mistake? Oh, sorry. I know what my mistake is. Tell me what it was. I didn't actually use my solutions. What did I leave out? I left out my J. That's a bad mistake. Okay, so we have okay, the √3 things are still gonna cancel, but now I'm gonna get minus √3 times √3 is minus 3 times j squared. So let me write this as minus 3 times j squared. That's what I left out. And then of course minus 3j squared is plus 3. And so we get x squared minus 2x plus 4, which is the original equation. Okay. So that's just a brief introduction to square root minus 1. What we'll do next time is we'll start to interpret this a little more deeply so that it can do more than just solve quadratic equations. And then we'll eventually work towards applying these to electronics types problems. All right, thanks very much.